So I'm going to present some comparison between observation and parameter-driven models for the Poisson model for time series of counts. This is a joint work with Migon from the Federal University of Rio de Janeiro and my colleague Marcos Prats, also from the Federal University of Minas Gerais. I'm going to give a brief introduction, so then I will show the main models we are going to present here from the parameter-driven class and the observation-driven class. And so I am going to show some empirical results, some simulations, and then an application to a real data set. This classification of observation and parameter-driven models is due to Cox in 1981. So he classified for non-Gaussian time series the observation and parameter-driven model for the general exponential family formulation. I am going to show the main difference between these two classifications, but this last one is mainly for models that have latent structures. So this is the classification. So if you have a time series, and this is the notation I'm going to use here. So all the observations till up to time t minus 1, and if theta t is a parameter, so in the observation-driven class, the parameters will depend, are a function of only of the series and the past times up to time t minus 1 and a random innovation here. And for the parameter-driven model, this parameter is a function of the parameters up to time t minus 1 and noise innovation. So this is the main difference. Here, the parameters are a function of the series, and here the parameters are a function of the parameters in the past times. So here we have a latent structure for these parameters. There are many models in this class of observation-driven models, but I'm going to talk just from the Gamma and Glamour models. The name is very similar because they are really very similar, but they were proposed almost simultaneously in 2003 by Benjamin et al., a work published in JASA, and Davis et al., another paper published in Biometrica. This paper from Benjamin, in fact, is a generalization of two other works here. The first one from Ziegler and Kakish, I don't know if this is the name, in 1988. So it is just a generalization of the general linear model. So they have put an extra component in the generalized linear model. And in this structure, you can model the correlation that are present in the time series. So they propose this model using an autoregression component. So it's an autoregression structure added to the generalized linear model. So in 1994, he generalized this work, putting a moving average component besides the autoregressive component. So it's like an ARMA model from Box and Jenks. And Benjamin, they just formulated the ideas of these two papers, and they proved some properties of the models, of this model. And the Glamour model started with Shepard in 1995, and Davis et al., they just generalized the model from Shepard. So I'm going to show the two models, and you will see that they are very similar. On the other side, the parameter-driven models, in the Bayesian perspective, you have the works of West, Hertz, and Migon, and Smith and Miller. And so they are just dynamic generalized linear models. And we have a work here in 2013 in the same direction. And from the classical perspective, there is this work from Zeger, again, in 1988. And there are also the works of Derby and Koopman for non-Gaussian time series, a very computational model using Monte Carlo maximum likelihood. Well, but in the literature, there aren't many works comparing these two models. There are some comparisons here in this work of Davis Weir and Wang in 1999. He shows the main difference between these two approaches, and there are some applied works here, especially from Young. He compares the models using many applications, bio applications, and he compares the models. These two approaches, not the models, the observation and parameter-driven approach. And so this is the objective of this work, to compare the approach using some simulations. So we did an extensive simulation study based on the conditional Poisson distribution, because it's easy to compare for this simple model here. We used a latent ARP process in the mean, so this will account for the autocorrelation in the data. And for the parameter-driven case, we used the Yin approach to estimate parameters. And for the observation-driven models, we used MC&C procedures. So now I'm going to show you the main models. The notation will be this one. So the previous information is given by the series up to time t-1 and all the covariates. We are going to use this conditional distribution as a Poisson with mean mu t. And we have the log link for the Poisson. So we have to estimate the beta parameters. We have m covariates. And this component here, this is the main difference between the GLM, the Generalized Linear Model, from these models that I am presenting here. We are going to put some structure here to account for the autocorrelation present in the series. And this is the component that will change from one approach to the other one. Okay, so in the parameter-driven models, I am going to use the proposal from Zeger. So this conditional distribution here, this is the latent process which introduces over-dispersion and autocorrelation into the series. So if we write this in this way and use the log link function for the Poisson, we have this model here. So we have here the conditional Poisson distribution, the predictor. So this component here in the parameter-driven model is given by an autoregressive structure here. And the noise here is has a normal distribution. Okay? So here we have to estimate the beta parameters and all the phi parameters. And the likelihood function is not difficult to write. So we have this multiplication of the Poisson and the normal distribution for the noise here. So we have to estimate this, and as we cannot write this analytically, we have to use numerical procedures, and we are going to use INLA here. The INLA approach, I'm not going to talk much about this, but it was proposed by Hu in 2009. it assumes that the observation belongs to an exponential family, as is our case here, with mean μt, and is linked to the predictor through the link function, so just what we have here. And it aims to approximate the posteriors with closed expressions, so it provides a great gain computationally if compared to MCMC methods. And it does not have problems of convergence. So we decided using it here. The observation-driven models, the first one is the Glamour Model, which was proposed by Benjamin. So we have the same conditional distribution. I put another notation here for the previous information, because here we have, besides the series up to times t minus 1 in the covariance, we have the mean of the series here, the mean of the process, up to time t minus 1. Okay. And here we have that same structure of the parameter-driven models, the conditional Poisson, the predictor with this component. But now this component is written in this way. So we can see that it depends on the series on the past times. So this is the main difference between observation and parameter-driven models. So it depends on the series, the covariance, and the mean of the process here. And if we think in the diagonal structure, we see that here we have something similar to the autoregressive structure and the moving average component from diagonal models. So here we have to estimate the p phi parameters and the q theta parameters. And this is just like a residual here. And for the Poisson, we need this restriction, because if we have 0 values for the series, we have to take logarithms, so we need this restriction here. By the other side, the Glamour model, it's slightly different from the Gamma, was proposed by Davis. It has the same structure here. So this, which is the ZT, is an infinite moving average component. And this noise here is given by some residuals. For example, Poisson residuals, which was chosen by Davis et al. To replace these residuals here. So they made this analogy with our models, so we can just write down this infinite sum here from for autoregressive and moving average components. So what we have is just the same thing here, and the ZT, which is this infinite moving average sum, will be an autoregressive component plus a moving average component here. And this residual here is given by the Poisson residuals. So this is the main difference between the three models. So the likelihood here is very simple to write, because we have the Poisson model, and for this we use the MCMC. Oh, sorry, here we have the likelihood, and for the MCMC we need some priors, and we can think of a normal multivariate distribution for phi, theta, and beta. And if they are independent, we can write it like this, or we can just use uniform priors with some restrictions, because these parameters here are supposed to be between -1 and 1 for stationarity and invertibility of the process. So we imply the Metropolis-Hastings algorithm here. Just showing some empirical results. We simulated an extensive Monte Carlo experiment with 10,000 replications when we have series of size 100, but we just tried also a very large series, 10,000 size 10,000, and we simulated the series from 3 scenarios. So the first one, when the series was generated by the EBEB model, the parameter driven, the other one, the series is generated from the Glamour model, and the third one, the Glamour model. And the Glamour model, I forgot this. We have this parameter lambda here, which is a bit complicated in this model. It complicates very much the maximization of the likelihood here. We just set it like equal to 0.5. So the first simulation, we just tried a pure autoregressive without covariates, just to see what happened with the models. So we have this simple structure here for the parameter-driven model. It's AR1 autoregressive model. For the Gamma, we have just here, and for the Glamour, we have this here. And we chose 3 values for the parameter phi, and this last one very close to the non-stationary region. Here are the main results, so I point out the main conclusions. The first one is that, as we expected, the estimation is better when for the model which generated the series. So if the series is generated by the EBEB model, EBEB, or the parameter observation, it gives the best estimation. If the series is generated from the Gamma, it gives the best estimation, and from the Glamour, the best one. So it's in bold here. But here we can see that the Glamour model has some problems when phi is close to the non-stationary region. It cannot estimate properly the parameters, even when the series was generated from the Glamour model. So we have this problem here. The second thing we can see is that the Glamour model gives the not the best one, but it's very satisfactory for all the cases. So when the ZEG is the model, it close to the real values of the parameters, or even if we have the Glamour model here, it's not so bad. So the conclusions are just these ones. So they are comparable, and the Glamour model has these problems here. But the ZEG model always overestimate the parameter when we have other DGPs here. Okay. And the problem with the Glamour model is that the likelihood presents some very peculiar behavior. For example, here, this is the series of size 10,000. So the likelihood function, this is the likelihood function for the Gamma and for the Glamour. So it has this maximum here in the real value of the parameter, but we have this here. So we have to take care when we estimate the parameters, because depending on the values we chose, we can just stay around here and we cannot find the maximum. I jump this one. This is the model with the covariate. We tried 3 different covariates, normal, 0, 1, or the covariate being a time series generated from AR1, or the covariate is just a trend. So this is the model with a covariate, and the same AR1 process here for the ZT component in all the models. We just try the same phi values and it's beta as 0.3. The main conclusion here is that, and this is a conclusion that the other authors who had compared these models, Jung, they have found this. The beta component doesn't change when the DGP is the seg or gamma or Glamour, it gives exactly the 0.3 value which we have fixed here. So it doesn't change the value of the parameter of the covariate. If we generate from a model with phi equal 0.4 or 0.7, so it gives exactly 0.3 here, or even the 0.95, so the parameter of the covariate, the estimates doesn't change. But here we have some problems because we just have the exactly value for phi when we estimate with the same model that we generate the model. So it happens for all these cases. And just I want to emphasize here that the gamma model tends to underestimate the phi parameter when the DGP is the other two ones. So it gets close here when it generates the same, but it underestimates. And this we will find in the application. So this is a simple application with a real data set. It's a series for respiratory disease in São Paulo. We have this response variable with the number of patients with disease in the superior airway tracts in São Paulo, monthly data, and we have this covariate. We tried other covariates, but they were not significant, and we tried also some seasonality, but it wasn't significant, so we just used this covariate here, which was good because it was the same of our simulation study. This is a scatter plot of the covariate and the response. And here we tried many different approaches here. So this is the parameter-driven and the two observation-driven models. And this ZT, we tried an AR1, an AR2, but the best one was really unbelievable, an AR1, which was the same as our simulation. So we fitted the models for the Ziegler, Gamma, and Glamour, and the best one in terms of AIC was the Glamour model, which presented the smallest AIC. So we fitted the parameters for this model, and here we see that the beta component didn't change much for the three models. In fact, it was not significant here for the Glamour model, it was strange, but the phi component was 0.6 for the Glamour model, and it was not significant here for the other two models. And here is what we find is most interesting, because if we just fit GLM, a generalized linear model for the series, and we do not account for the autocorrelation present in the series, we cannot find white noise residuals. We always find some peaks here, significant peaks on the residuals, saying that the model is not well adjusted because we have some autocorrelation residuals. So we can make the residual series on white noise when we fit this observation or parameter-driven models which account for this autocorrelation here. So we are glad that this happened. And okay.